In the summer of 2022, a ship left the port of Rotterdam carrying a cargo that would define the next century. It wasn't carrying oil, it was carrying a wind turbine, a single blade, over 100 meters long, a sleek curve of fiberglass and resin destined for a North Sea wind farm. Its journey was tracked by environmental groups and celebrated in press releases. It represented the future, and every single mile of its voyage was powered by heavy fuel oil. The tug that guided it, the cargo ship that carried it, the trucks that would take it ashore, all ran on the very thing this technology was built to replace. This isn't an irony, it's a dependency. The entire apparatus of the energy transition, the physical infrastructure of a greener world, is being built by and with the old one. This is the Energy Historian, uncovering the hidden systems that power civilization. We are told we are in an energy transition. The numbers seem to confirm it. Global investment in clean energy now surpasses $1 trillion a year. Electric vehicle sales are climbing. Solar panels are being installed at a record pace. The narrative is one of replacement, of swapping out dirty fuels for clean electrons. But if you follow the physical supply chain of this transition, a different story emerges. It doesn't start in a Silicon Valley design studio or a government policy office. It starts in a mine, a massive open-pit mine where 100-ton trucks haul raw earth. Those trucks don't run on batteries, they run on diesel. The excavators, the crushers, the processing plants, all diesel. To build a single electric vehicle battery, you need to move over 250 tons of earth. That movement is fueled almost entirely by oil. The green future is a massive consumer of the fossil present. This is the first hidden layer. The transition is not a clean swap. It's an addition. We are not replacing the fossil fuel system. We are building a vast new energy system on top of it, using the old system's power to do so. Think of it as trying to build a new ship while you're still sailing the old one across the ocean. You need the engine of the old ship to power the saws, the cranes, the welders that are constructing the new vessel. And if that old engine sputters, both ships slow down. Every solar panel factory, every battery gigafactory, every wind turbine assembly line is an industrial facility. It consumes immense amounts of power and heat, often from the local grid, which in most of the world is still fed by coal and gas. It requires materials transported by global shipping, which is 99% reliant on oil. The transition's physical backbone is made of fossil fuels. Now, the scale makes this dependency terrifying. The International Energy Agency estimates that to hit net zero by 2050, we need to mine and process staggering amounts of critical minerals. Lithium demand must grow over 40 times by 2040. Graphite, cobalt, nickel similar multipliers. This isn't a gentle ramp-up. It's the largest re-engineering of material supply chains in human history. And the machines that will do this mining, this refining, this transporting are not electric. They don't exist yet. The world's largest mining truck, capable of carrying 400 tons, would need a battery weighing over 40 tons itself, a self-defeating loop. So for decades to come, scaling the green future means scaling diesel consumption in mining. The bottleneck isn't willpower, it's horsepower. Let's follow one material, copper. A single electric vehicle uses about 3 times more copper than a conventional car. An offshore wind turbine uses over 8 tons of copper per megawatt. The wiring, the motors, the inverters, all copper. To meet projected demand, we need to open new copper mines the size of which the world has rarely seen. The problem? Copper ore grades are falling. A century ago, miners might find rock that was 2% copper. Today, it's closer to 0.5%. This means moving exponentially more rock for the same amount of metal. More rock means more diesel. More diesel means higher costs. And this creates a perverse feedback loop. If oil prices rise, the cost of mining copper rises. That makes EVs and wind turbines more expensive, slowing their adoption. The price of the new system is set by the old one. We built the fossil age on cheap energy from oil. We are trying to build the post-fossil age using that same cheap energy. But what if it's not cheap anymore? This brings us to the second, deeper layer, petrochemicals. Even if we could magically electrify all transportation and generate all electricity from renewables tomorrow, our dependence on oil would not end. It would just change channels. Because oil isn't just gasoline, it's the feedstock for modern life. It's the chemical building block for almost everything that isn't metal or wood. Look around you, the insulation in your walls, the synthetic fibers in your clothes, the asphalt on your roads, the plastics in your phone, your computer, your medical devices, the fertilizers that grow half the world's food, the lubricants in every machine, including wind turbines and electric vehicles. There is no such thing as a solar panel without petrochemicals. The polymers that encapsulate the cells, the sealants, the lightweight composites for frames, all oil-derived. The green economy isn't just powered by oil, it is literally made of it. This is the core structural truth that inverts the initial question. The world isn't going green, despite still depending on oil. The world is going green because it still depends on oil. The fossil fuel system provides the essential material and energetic surplus required to build its own successor. It is the parent, the midwife, and the life support system for the new energy age. This creates a profound temporal trap. To build enough renewable infrastructure to replace fossil fuels, we must first burn vast volumes of fossil fuels. This burn rate is not a side effect. It is a prerequisite. The transition's carbon budget includes the carbon cost of building itself. Now consider the most visible symbol of the transition, the electric vehicle. It feels like a clean break, but its existence is a tapestry of global oil dependence. The lithium may come from Chile, pumped from brine pools using diesel pumps. The cobalt may come from the Democratic Republic of Congo, mined by diesel equipment. The nickel may come from Indonesia, processed in coal-fired smelters. These components are shipped to China on oil-burning vessels for battery assembly, then shipped again to Europe or America for final vehicle production. At every step, the leverage of oil is absolute. A spike in diesel prices doesn't just raise the cost of driving a truck, it raises the cost of every single link in the supply chain of the alternative. The system's greatest vulnerability is that it must accelerate the very thing it seeks to replace. History offers a stark lesson in material leverage. Look at the 1970s oil shocks. The immediate crisis was about gasoline lines, but the lasting shock was economic. The price of everything made with or transported by oil skyrocketed. It triggered stagflation, a combination of high inflation and high unemployment that economists thought was impossible. That was the shock from a 10% supply disruption in one commodity. Now imagine a world intentionally trying to constrain oil production to meet climate goals, while simultaneously demanding more of it to build alternatives. You create a supply crunch within the system, building the escape hatch. Prices for oil would rise, making mining and manufacturing and shipping more expensive, slowing the transition, requiring more time, during which you keep burning oil for everything else. It's a self-strangulating loop. The green transition is the largest industrial project in history, and its supply chain is the one we already have. So where does this leave us? With a paradox that is not a failure of will, but a law of physics and systems. You cannot build a complex industrial civilization without an immense surplus of dense, portable energy. For the last century, that surplus came from fossil fuels. To build a new system that doesn't use them, you must first borrow heavily from the old system's energy bank. The transition, therefore, is not a simple switch. It's a bridge, and the construction of that bridge is the most oil-intensive endeavor of our time. The goal is to reach the other side before the borrowed energy and materials become too expensive, or the climate consequences of using them become too severe. It's a race against the very tools we are using to run it. This reframes every headline. A new battery breakthrough isn't just about chemistry. It's about how much diesel is needed to mine its components. A new wind farm isn't just about clean megawatts. It's about the oil-burning ships that installed it. The system's progress is measured not just in gigawatts installed, but in barrels consumed per gigawatt. The leverage point is no longer just the power grid. It's the global network of tankers, mines, refineries, and chemical plants that feed the entire industrial metabolism. Stability in the old system is the precondition for building the new one. If the oil system stumbles, the green transition doesn't just slow, it fractures. Most people assume the biggest risk to the energy transition is a lack of political will. After understanding this system, what's the one factor you now see as the most fragile link? Drop your answer below. The hidden infrastructure is always there. Now you know how to read it.